more examples of that. And then we're done as far as the lectures, because we have a testing next Wednesday. So next class, I will do few more examples that's left from the other lecture notes, and then we can just have question answer or review session for next class. The only topic is left is just what we call independent or what we call random variables. Sorry, we cover independent. Random variables is left, which is really a short lecture, and that's just really the last topic that we are learning, and then random variables. We discussed a little bit about conditional probability. This is basic, what was the definition of what we call conditional probability, and a few examples, okay? So the first one is saying, think about your, imagine a couple with 2 children, each of whom is equally likely to be a boy or a girl. Now, suppose you're given the information that one of this is a boy. So one is a boy. What is the probability of the other one to be a boy? Sorry. So this is saying, according to this picture, you're having, so figure on the left shows the 4 equally likely combinations of the gender for children: boy, 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 girl, girl, boy, and then girl, girl. The combinations, one of the children to be boy is the gray area, and the combination one of the other child must be boy also is blue, gray. Given that you know one of the child is a boy, only there are 3 combinations in gray region could be a case. So you can think about the set of those outcomes, a new sample space of the elements, and then what is the question? The question is saying, according to this information, what is the likelihood of the second child also to be a boy? What is it? One out of?
Excuse me.
One out of? So your total gray area is the chance of having one to be at least a boy, okay? So the total cases are 3, that one of them are boys, but then you want to have both to be boys, so it's just a boy, boy out of the 3 cases, 3 other combinations that's possible, okay? So that's actually coming from this formula. So we don't need to guess, we don't need to think, because here is saying, if you're looking for a conditional probability given F, so means you're looking for second child to be a boy given the first one is a boy, okay? So it's going to be probability of intersection divided by the probability of the F. So probability of intersection divided by probability of, so intersection for your case was what? So probability of E and F, so E is the second to be a boy, F is the first one is already a boy. So your intersection is
the first ones are in boy.
So E is the event in this case. So what you're looking for, the second to be the second child to be boy. And then F in this case is the event, the first child is a boy. The chance of the first child to be a boy is the probability of the first child to be a boy is 2 out of 4, right? And then probability of the intersection. So what is the intersection?
The first and second.
So
Are you looking for the numerical value of what the intersection is?
actually, it didn't say the first one, sorry. It says, yeah, actually, I'm reading the yellow part. It says, now the given information is one of this is void. Okay, so it doesn't say it's first or second. So that's why it's not 2 out of 4, it's 3 out of 4, sorry. Does it make sense? So that's not saying first or second, it's just really one boy. And the intersection, as you say, both of them to be boy is just for 1 out of 4. So according to this formula, you're having the intersection, which is 1 out of 4. And then one of them, which is 3 out of the 4. So that's why is 1/3, according to this one. Sorry. So let's try more examples. Here it says the probability of getting the sum 10 for 2 fair dice. So you're having 2 fair dice. What's the probability of the sum of the 10? One, two, three, four. 1, 2, 3, 4, 5. Then 6. 1, 2, 3, 4, 5, and 6. Okay, so what's the probability of the sum to be 10? So your sample space, as you see, is the sample space, as you see, is 36. So you have total of 36 different outcomes. And then your event space, which is sum of 10, I will just write it over here. So your 6 and 4, right? 5 and 5, and then 4 and 6. Okay, so that's the case. So there are 3 cases. Do you agree? So then probability of sum 10 is 3 out of 36. So it's 1 out of 12. I can release it over here. It was sum of 10, right? So it was just 4 and then 6, 5 and 5, and then it was 6 and 4. Okay, so there was 3 cases only. So now find the probability of getting the sum 10 given at least one of the dice is 5. Probability of sum of 10 given at least 1 5. I'm going to follow the formula. Probability of sum 10 intersected by at least 1 5 divide by probability of what's the denominator? F at least 1 5. So what's the number of cases that you have? What's the limited sample space which you have one of these 5? Which one is one of them is 5? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have total 11 different outcomes for total 11 outcomes for at least one of them to be 5. Okay. And then what is the intersection? Which one is the intersection?
At least 1, 5,
And some 10. It's 1 out of 36. So it's going to be 1 out over 11. Agree? One more time. A pair dies, one blue and the other one gray. What is the probability of the sum of the numbers showing is 8, given both numbers are even? Given both numbers are even. What is the number of cases that both are even? How many cases both are even? Am I right? 1, 2, 3, 4, 5, 6, 7, 8. I didn't write 4, 4. 9. So you have 9 chance out of 36 to be both even. And which one has the sum of 8, which is the intersection? How many of them has the sum of the 8? 1, 2 only. Oh, 3. Right? Right?
yeah.
I'm okay now, right? 1/3. Question here? Do you agree with this? That's just a problem that we tried many examples in the previous class. So this is saying about what we call false negative for a test and false positive. There is a condition called BO suffered by 10% of the population. There are no prior symptoms. Victims just suddenly start to stink. Fortunately, there is a test for before things start to smell. The test is not perfect. However, if you have the condition, there is a 10% of the chance the test will say you do not. So that's a false negative. And if you don't have the condition, there is a 30% of the chance the test will say you do. So that's a false positive. So what's the question? If the test is positive, then what is the probability of the person has the condition? The person is actually sick. Can you complete your tree because we made it a few times in previous class? Okay. Can you give me my numbers? What is the chance to be sick? What is the chance to be sick? 10%. So not to be sick is 90%. What is the chance to get what's given? False negative. False negative. 10%. And then what's the chance for false positive? 30%. Do you agree with my branches? So the rest of 90% goes there. The rest of 70% goes there, okay? So if I want to follow the rule that we just learned, so let's write, you're looking for, if the test is positive, so if you're looking for, then this has the condition. So has the BO given, given the test is positive. So according to what we just learned, you need the has BO intersection with the positive on top. And then you need the test positive on denominator, okay? So I'll write the test positive here. And then has the BO over here, and then we'll see which one is intersection. So the test to be positive, your test to be positive, you have one chance of product, right? So 0.09 over here, that gives you a test positive, and then 0.027 right over here. Okay, that's the test to be positive. So for the test to be positive, you have either this case or that's addition, right? So you have either the top, which is the true positive, or the bottom, which is the false positive. So that is the total. And then which one is the intersection? Which means the person is sick and the test is positive. The person is sick and the test is positive. This is really the only case, right? So that's the top of your fraction. And that shows how the test is horrible, right? Because you get the 1/4, 25%. You can trust your test only 25%, right? That's what it says. If the test is positive, what is the probability of the person is actually sick? 25%, which is really horrible, right? In reality. Okay, can we try one more time? This needs another tree. A bag contains, do I have any question on top one, guys? I was okay, right? No? Okay. So you're having a bag which has 5 blues and 7 grays. 2 randomly chosen. So you're without the replacement. Find these following probability out of the diagram. So you make your tree diagram first. So you start with the choosing, blue or gray, and the second choosing blue or gray, and the second choosing blue or gray. at first step, what is the chance of getting blue out of the bag? Blue is 5 out of 12. Thank you. Gray? And then in the second step, because there is no replacement, what would be the chance of having the second one to be blue? Okay. And then what's the chance of having the second to be gray? Great. And then the first choice was a gray. So what's the second one to be a blue? $11. No, you have one less. And then gray. Okay. So then we are listing what the question asked me to do, probability of blue and then blue. Probability of blue and then gray. The probability of the first ball to be gray and then blue. Probability of the both gray, okay? Which is the product rule, right? So because it's a step by step. So 5/12 times 4/11. 5/12 times 7/11. 7/12 times 5 times 5/11. 7 out of 12 times 6 out of 11. This is really fun. This type of the problems that you can just set up a tree for that and just product of each branches and test for intersections, test for all of the possible cases. They are really fun. What is the probability of the second ball is blue? What is the probability of the second ball blue? Second one to be blue. So is either this one or this one. So either is 20 divided by 132 plus 35, 132. Because or, either or, so that's why you have to use the plus. Okay. What's the probability of at least one of them to be blue? At least one of them blue. You're having, what did you say?
The two middle ones.
At least means one of them or two of them, right? At least.
Oh, so plus 3 of the sums, 20 over 132, 35 over 132, and then 55 over.
Even you can just write probability of at least one blue is complement with the probability of no blue. That works too, right? So which is 1 minus 42, which is still the same answer. By complement also works. Make sense? Question here? And we did once this kind of the what we call inclusive exclusive rule. It's the probability of probability of union is going to be probability of each minus intersection, right? So we did one in the previous event. I showed you, you had a quiz about that one. So now we want to practice the example. So one more time, is saying probability of either E1 happens or E2 happens is the same as probability of the first one plus probability of the second one minus overlap. That's what it says. So the question is, what's the probability of getting doubles, two of the same numbers, or sum of 6? What is probability of getting doubles? What's the probability of getting doubles? Can I move on that things? Doubles, I think, yeah. 36. Oh, I mean, you divided, okay. That's fine. You simplified, right?
Yeah.
Okay. So then the probability of having doubles is going to be either 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5, and 6, 6. So you have 1, 2, 3, 4, 5, 6 cases. And then what was the sum of 6, huh? It was sum of 6. So if you're looking for sum of 6, it could be 4 and 6. Sum of, what was it? Sorry.
And the sum of 6.
Oh, sum of 6. Okay. Let's just check what's the sum of 6. So sum of 6 are 4 and 2, 3 and 3, and 4 and 2, and then 5 and 1. It's this one, right? Okay, and that is giving me a 6 out of 36. The other one, 1, 2, 3, 4, 5. Probability of having doubles was 6 out of 36. Probability of sum 6 was 5 out of 36. What's the probability of intersection? What was the probability of intersection? It was really one case, right? So one intersection. So that is going to be probability of first union second equals probability of the first one plus probability of the second one minus probability of the intersection. So that is going to be 6 out of 36, 5 out of 36 minus 1 out of 36, and 10 out of 36, or 5, 80. Makes sense, huh? Agree? Any question here? So there are the cases that you do not need to subtract from the intersection. What's the reason? Because they are mutually exclusive. So if they are mutually exclusive, you don't subtract from the intersection because basically the intersection is 0, right? So like this problem, your probability of getting doubles that you already know what is it. And that was probability of getting doubles was 6 out of 36. Probability of sum 5. Let's go back to see what's the probability of sum 5 on that chart. Okay. Probability of sum 5 is 4 and 1, 2 and 3, 3 and 2, and then 1 and 4. Okay, so 1, 2, 3, 4. So it's 4 of them. So it's 4 out of 36. But do I have any case that I get the double and then the addition is just 5? No, there is a 0 case. So that's why they are mutually exclusive. That means you can just probability of event 1 union event 2 is going to be only addition of the probability of each one, which is 6 out of 36 plus 4 out of 36. Okay. Question here? Any question here? Okay. In the last class, actually, I stopped right on the independence. Okay. I was trying the independence. I was trying to just explain how do you test if two events are independent. Okay. So we'll have some examples here, and then we'll practice the one that we were doing in the previous class because we stopped at those rules of being independent. Okay. And we had the same example. It says if you're having two coins which you're tossing twice, the outcome of the first toss does not depend on the outcome of the second toss because they are completely independent. Let's define the event A to be ahead on the first toss and the event B to be ahead on the second toss. So these are two events that we define. We want to check whether they are independent or not. So if you're having event A, so this is the test we saw in the previous class. Okay, so it's saying if you have a probability of A given B and they are independent, it's going to be probability of only A. If you have probability of B given A and they are independent, so that is going to be probability of the B. This is the test that we've seen in previous class, and we'll practice more on that same lecture note again, okay? So now I have to get the probability of each of A and B and test it, whether satisfy that equations or not. So what's the A? Event A is defined, the head is obtained on the first toss. So your A is either head or head tail. And then probability of the B is which one? A head is in the second toss. So it's going to be head or it's going to be tail head. And then the intersection is head for this one. So probability of A happens. Your A or B happens, it doesn't matter. So you have of two cases out of the 4 possible cases, right? So the total or sample space is 4. So you have 2 out of 4. So it's going to be 1/2. You have a 1/2 of the chance to get the first try to be head or the second try to be head, okay? So if I want to follow the formula, what's the probability of A given B? It's going to be intersection on top divided by probability of the B. Your intersection is only one element, 1 out of 4 possible cases. Divide by 1/2, so it's going to be 1/2. So probability of B given A the same. So you just do the intersection and then divide by A. So intersection is 1 case out of 4 possible cases, and that A or B was 1/2. So that is 1/2. What it's trying to say, probability of A given B is the same as probability of A. And that means they are independent. Probability of B given A is the same as probability of the B. That means there is no relation, they are independent. One of them, the one event has nothing to do with the other event because this passed this equation, it passed this test. Okay. Makes sense by now? So that was one test that we've seen in previous class, and I will see it again. The other test says if they are really independent, probability of these two happens at the same time is going to be the product. So if they are independent, probability of these two events happen at the same time is going to be the product of these two. So this is again about tossing coins. So tossing coins are really independent. So if you get head or tail in one coin, it does nothing to do with the other one to be head or tail, okay? Find the probability of event head on first toss, so then tail on the second toss. 50-50, but then it's the probability of and. What is the and? Head and then tail. So it's probability of having head times probability of having tail. So it's going to be 50-50, as you said, means. Agree? Okay, so can you try the next one? There are two students in the final exam. The probability of one of them pass is 70%, the other one pass 95%. They are independent. Passing these two people or two students are independent event. What's the probability of Joey pass and Alicia pass? Sorry, or. Sorry, or. Yeah, then highlighted in blue. The union, right? So it's the union, so it's going to be probability of first, second minus subtraction. Sorry, minus intersection, but there is no intersection, right? Because they are in. No, there is intersection. There is intersection, right? They could, yeah. So you can have both pass. So what's the intersection?
That they both.
Yeah, because that is independence. So it's going to be product of the probability of each one. So you subtract from the product. Make sense? So probability of the first person pass or second person pass is the same as probability of the first person pass, and probability of the second person pass minus probability of both pass, which is the independence means product of this probability. So since they are independent, it's going to be product of these probability. So that was 70% of the chance, that was 95% of the chance, and that was 70% times 95% to pass. Whichever, okay? Changes. Anyone has the number? No? 98? 5? I'll give you this one. Okay. And one more time. You're having loaded coin this time. The chance of head is 60%. The chance of tail is 40%. Suppose the coin toss twice. They are independent. They are independent. So is asking what is the probability of obtaining two heads in two toss? What is the obtaining two heads? Probability of head is going to be probability of head times probability of head, which is going to be, okay, 86%. And then what is the probability of obtaining one head? One head means head tail or tail head, right? So it's going to be probability of head tail or tail head. Do I have any intersection to subtract? No, right? No, right? So then it's going to be probability of head times tail for the first one, probability of tail times head for the next one. Agree? So 0.6, 0.4, 0.4, 0.6. Okay. What is the probability of 2 heads and what's the probability of at least 1 head? 2 heads and 1 head. At least 1 head. Probability of no hits. No hits is 10, so it's 24.4, yes. And then what's the next one? Probability of at least 1 hit. Complement. At least 1 hit is complement of no hits. No, yeah. Okay. We can go that way, or we can just say 1 minus the other one.
So it's moving.
Well, they are completing, right? Probability of tail is going to be 0.4 times 0.4, which is 0.16. But then at least 1 head is complement of that. You can go directly because it's not really a big sample space. Okay. Question here. The next one is more fun, huh? It's you're tossing 10 times. This time you're tossing 10 times. So this is more fun. What's the probability of obtaining 8 heads? Point 6 to the power of 8, and then not plus, because you need 2 more sedation. So it's 0.42 times. That's it. How about the displacement? How about if you're having different heads? Because we didn't say the first one ought to be heads and then the last 2 to be. All right. So what I'm saying, if you're saying this is 1, 2, 3, 4, 5, 6, 7, 8, and then this is different than 1, 2, 3, 4, 5, 6, 7. How about that one? How do I consider that case? So you're okay with that 8 many times, that 2 times. How do you explain the displacement, which gives you different order?
Change though, because it's the same probability.
That's just, if the question asked me this or the next one or the next one, so that gives you this many chance, sorry, probability to happen. That gives you this many chance to happen. and then so on, okay? But you're having either that case, or that case, and then so on. 8 out of 10 or 2 out of 10? Yeah, because either 8 heads to be selected out of 10 places, or you should have 2 tails selected out of 10, which is the same, okay? So now the next one is better. At least 8 heads. Actually, since it's similar to the previous one. What is it? At least 8 heads, and then if you, I think that way is easier. 8, 9, 10 is easier than going back.
You summed it all.
This is for exactly 8 heads. No.
If we sum it.
Right. Would the conflict be at most 2 bits? You do 1 minus at most 2 bits, or that not will work?
Oh, you mean 2 tails?
Or 2.
So at least 8 heads.
But if we summed also, because I mean, that the part you gave us a portion of the answer for if we got 8 heads, but then if we also solved that for 9 heads and 10 heads and summed it, would that be the way to go?
That's one way to go. But I think Kyle was thinking about something else. That works too.
I was thinking of like how we did part B on the third question. How it's 1 minus b, but considering this is 10, 1 plus not 2.
It's too much, right? So if you have at least 1 8, so then it's going to be 8, 9, 10. But if you want to go with the complementary, so that's going to be 1 minus all of the cases that you might have: 1 heads, 2 heads, 3 heads, and 4 heads, and 5 heads, and by 8. So that way is longer.
So that would be a lot.
Yeah. So then probability of 8 heads, you got it already. You just have or probability of 9 heads, and then or probability of 10 heads, which is going to be the same 8, 10, 0.68.4 to the power of second. So then you have 9 out of 10, 0.6 to the power of 9 and 0.4 one time. And then 10 is 10 out of 10, which is one really case. 0.6 to the power of 10, and then 0.4 to the power of 0. That you don't need to write it down. Do you agree with the argument? Okay. Question here? Is it a small? Which?
Yeah.
Like it. Can I move on? Okay, so let's just move on to the one that we were doing in previous class and finish the examples of that lecture note. We have a few left. So I was listing the independence events over here when we stopped the previous class. So there is, I think, a few examples here to practice exactly the rule or the test for being independence. First one says, in this loaded die, which is tossing twice, having 6 has more chance than 5 other, which is explaining, for this dice is explaining getting 1, 2, 3, 4, 5 is 1 out of 7, getting 6 is twice chance, so it's 2 out of 7. And then the question is part 1. What is the probability of the first roll? So what's the event? Sorry. The loaded die is twice as likely to come with this. The probability of distribution looks like this. The loaded die is rolled. Oh, so that's what's happening. So the loaded die is rolled twice. Okay. So what's the probability of the first roll does not come with the 6? How many? Not 6.
Oh, not 6. So 5 out of 7.
First, not 6. Right, 5 out of 7. And then what's the probability of the first not 6? And second one to be 6.
2 out of 7. Oh,
First not 6 is 5 out of 7.
yeah.
Second one, 2 out of 7. Agree? The product. How about number 3? The probability of exactly one of these two rolls, 6.
Is it 2 roll?
Exactly one of these two rolls comes 6. The first case is, so this is problem 1, this is part 2, and we're doing part 3. So the first is really like part 2, right? So exactly 1 to be 6 means the first one not 6, and the second one to be 6. So this is the first one. Or the other way, the first one to be 6, and then the second one not to be 6.
20 out of 49.
So for first one to be not to be 6, you said 5 out of 7 times the second one not to be 2 out of 7. First one to be 6 was 2 out of the 7, and then second one not to be 6 was 5 out of 7. Yes, is 20 out of 49. And it's saying everything is possible. So if you are having just really all mutually independent events, the intersection of as many you have, the intersection of as many events you have is going to be the product. So this is notation P capital stands for product of your probability of each one. So we don't have that many, but if you have had more, it's just really mutually independent means always your probability of intersection is product of the probability. It doesn't matter how many you have, as long as they are independent, it's going to be the product. So probability of any of this one, if they are independent, is the same as probability of this one with the any of ij not to be the same. So that's the rule of independency. I have one example that I can test the independency events. So the way that I've done, actually I've used this test, but I could use this test also to make sure they are independent. Okay, this is one example here. your question asks you directly whether these two events that is defined over here are independent or not. So that means you have to apply the test, one of those 4 tests, to see whether they are independent. The one that I have applied was this one. This one I just test, but again, it could be any of those 4 listed tests that we had at the beginning, okay? So what is the event? 10 kids are randomly grouped into the team A and B, which 5 each. And there are 3 kids in a group, Alex and his 2 best friends, Jose and Carl. So we define the event J, Alex ends up at the same team as Jose. The event C, Alex ends up on the same team as Carl. Are these 2 independent? Again, the steps are this thing. I'm going to just show by that rule they are independent. They are not actually independent. They are not actually independent, okay? So what's the probability of Jose happens? What is the probability of Alex ends up on the same team as Jose? Probability of Jose and Alex to be in the same team, divide by the total probability, total sample space. What's the probability of Jose and Alex to be in the same team? 1, 2, 3, 4, 5 people in a team. 1, 2, 3, 4, 5 to be in the team. So you can select Alex and then Jose. Then you have 3 other people to choose. To choose out of how many?
Yep.
2 of them already selected. And same thing, if you choose Jose and then Alex, you have 3 other people to choose out of the remaining students. So you are having 2 possible 3 out of. I don't know, in my solution, I have 3 out of 5. I have, no, that's 8. No, 5 can't be true, it's 8. Okay, what's the sample space? Selection of 5 for a team out of 10. Selection of 5 for a team out of the 10. Okay, that's the sample space. And actually, since I have the simplified answer, it's ending with the 4 divided by 9. And then just based on the probability of Jose given Carl, is going to be probability of Jose and Carl divided by probability of Carl, okay? So we need the rest. What is the probability of Carl? Actually, it's similar, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So Alex and then Carl and then Alex. You have 3 out of 8 left, then you have 3 out of 8 left. So Carl is 3 out of 8. So it's very similar to the Jose. But what's the intersection? What is the intersection of Jose and Carl? And what's the possible selection of 2? 2 more students out of 7. So 2 out of 7. But how about displacement of these people? You have a 3 factorial displacement of these 3 people. Do you agree with me? That is making this. And actually, since I have the simplified answer, I can copy. So this end up with the 3/8, which is not the same as this, which was 4 out of 9. So the J and R are not independent. It looks weird. Why not independent? That is really weird. But even if I use any other types of just like saying probability of intersection has to be the probability of first one times probability of the second one, that also fails, right? So probability of J intersected by that was 2 out of 7. And then 3 factorial, which is not the same as probability of 2 selection of 3 out of 8 for Jose, 2 selection of 3 out of 8 for Carls. Even if I use another test, this is alternative way, it doesn't pass. That means they are not independent because it's not the same as product. The intersection, probability of intersection is not product of probability. Question here? The last one is very quick and short, comparing the one that we did in the other lecture notes. A bias coin 10 times flipped, and then the having hits, probability of having hits is 1/3, probability having a tail is 2/3. What is the probability of every flip comes head? Which is 10. And what is the probability of 5 heads and 5 tails? All of the first 5 heads, and then all of the last 5 is tail. This is similar, right? We did the same problem. That is very similar to the previous one. The first is head, the rest is tail. And I don't have displacement anymore like a previous problem I tried, because it says exactly the first one all to be heads, or the first, so it doesn't say to be 3 heads or to be 4 tails. It says the first one to be heads and the next one to be tails. So that's why I don't have those displacement anymore. Make sense here? Any question? I think I have some nice problems on top also, but not that much nice. A little bit nice. Okay. Again, as I said, the last thing that we cover in this course is just the random variables, which is after your midterm. As far as the topics, the one that is in the test, we covered everything, okay? So then the next class, I think I have 2 more examples to practice, and then it's just going to be review, okay? Question here? I'm going to stop here.